OK, perfect. OK, great. Let's get started. So hopefully everyone had a great Easter break. Now let's try to start learning about databases. So let's try to refresh our memory about what we know so far, what we have been learning before the Easter break. So essentially, we have been talking about how to build a computer system to manage information or manage data. And there are so many different pieces of data like in the universe. And in this course, we have been focused on a very kind of ancient way of representing our data. That is by putting our data into something that looks like a table, right? If you look at this table, the structure is, OK, so the whole bunch of attributes, whole bunch of columns, right? Whenever we are looking at a table, the property of every single column is every single value you put there must have the same data type. And then every single row in this table, right, contains the instance of the relationship between multiple values, right? So this is our basic assumption about the data and knowledge that we are trying to manage. So more precisely, we introduced relational model. Essentially, it contains a schema of the database, which is a set of relations. For each relation, you have the name, you have a set of attributes, or columns, or field, whatever you want to call it. For each field or attribute, you have the name and you have a domain, right? Essentially, if you want to represent a student relation look like this, right, you can just write down the schema that's corresponding to essentially a table with only the header, not the content. And then we also define what is essentially a relational database instance. And then we also talk about a whole bunch of ways that you can actually query your data that is already represented in the relational form. We talk about query languages that are more theoretical, for example, relational algebra, right, and also relational calculus, right? One is imperative, another is declarative. And we talk about their relationships, right? So relational calculus is more powerful than relational algebra. And then you can start to constrain the semantics of relational calculus to make it equivalent to relational algebra, called domain-independent relational calculus. And then we also talk about different subsets of this. We talk about relational algebra with only selection, projection, join, and renaming. We talk about conjunctive query, right? And then we talk about more practical query languages, which is SQL. We talk about the kind of simpler construction, select from where statement. We talk about a larger subset of SQL. And then we talk about a whole bunch of other things you can do in SQL. So essentially, if you think about what I've been learning before the Easter break, we are actually providing a whole bunch of ways that you can use to query your data and try to get insight out of your data. And if you think about what actually happens under the cover, is in the middle, you have your database system, right? Hopefully, right now, you know how to query it. On the right-hand side, you as a user, and then on the left-hand side, you have your hardware. You have your hard drive, you have your memory, right? So how we interact with the database system as a user is a user going to say, OK, let's write a SQL query to create a table. And then what's going to happen is the database system going to create a table for you on your hardware. And then whenever the user provides a query to say, OK, I want this piece of data, what the database is going to do is bring the data all the way from the hard drive, where it's actually stored the data, to your DRAM, and then back to the user. So the design goal of a database system is to make sure, as a user, you do not need to worry about anything happen on the left-hand side. That is, how the database system is going to bring the data to you is not the job of the user. Instead, it is actually the job of the system to really automatically do that. So this is what we know before Easter. And then starting today, the thing we are going to do is to really switch gear and try to do not think about yourself as a user of a database system, and try to think about yourself as the builder of a database system. And today is the day we are going to open up this box. And we are trying to understand, if you give me a SQL query that you want to answer, how does the database system actually bring the data from the hard drive all the way to you as a user? So we are going to open this up. Essentially, we are going to talk about database system for the rest of the semester. So in this lecture, we are going to give you a very high-level overview about database systems to try to understand what are the different components inside the database system. And then we are trying to focus on one of those components, which is the disk manager. So that's what we are going to talk about today. So starting kind of on Friday, we are going to actually talk about different components inside database system. Okay, so database system is a very complex piece of software. People started building that 50 years ago, right? So we cannot cover everything, so we need to have our focus for this course, essentially the scope or assumption we have on the system we are trying to build. So essentially, if you look at database management system in real world, it could be really complex, right? So in this course, our mentality model so far is, okay, you have your laptop, you have your hard drive, you have your DRAM, right? So if you look at database system in real world, this is the database system, okay? So sometimes your data is stored in a whole rack, okay? When you actually buy something from Oracle, this is what you get, okay? So essentially, it contains a whole bunch of machines, contains hundreds of terabytes of memory potentially, right? So probably not 100 terabytes, but a couple, like 100 of terabytes of hard drive, right? So and terabyte of DRAM, right? Tens of machines. Together, they form a database management system. So of course, right? So this is something very hard to build, right? We are not going to talk about the whole thing in this course because we can spend actually the whole course talk about how to do distributed query processing, for example. So we need to scope ourselves a little bit. So in this course, we focus on relational database systems that have a disk-oriented architecture. So that is, we are assuming all your data are stored on your hard drive. So this is actually an assumption. If you look at database system you have today, it's often the case there are a lot of systems actually try to store the data completely in memory. So there's a whole bunch of in-memory database system, right? So sometimes you have some fancy hardware, for example, NVMe, right? For example, you can actually have data stored there, for example. So we are assuming all the data in this course are stored on your hard drive. And we are assuming, which is a very weak assumption, that is your disk, your hard drive, is actually larger than your memory, okay? So, and then we are also assuming your disk is slower than your main memory. So essentially, we also assume disk favors different access pattern. For example, if you have a screenshot scan of your data, right? You are reading data like in a consecutive way, right? So on your hard drive, it's faster. We don't have a random access on our disk, right? So that's going to be slower. So these are the 4 basic assumptions that we are making in this course. And then we are going to assume that all of these 4 things are going to be true. And then we are think about how to build a database system, right? In practice, when you talk about when you are really build your new generation database system all by yourself, so sometimes people start to attack each of these assumptions. And you can alter any of those assumptions. So you have a very different, and not very different, but a different database management system, right? So the goal of this course is really try to teach you, giving a collection of assumptions, how to think about the process of building a database system. So this is the assumption that we have. So if you think about real-world database systems, they often look like this. This is the one from IBM. This is the one from Oracle. They are very complex software systems. So in this course, we are going to simplify it. We are going to actually keep most of the major components of those systems. So the way we think about system look like this. At the bottom, all your data are stored on your hard drive. Essentially, every single relation inside your relation database are stored as a whole bunch of files. Okay? For example, you have 2 relations, file 1, store relation 1, file 2, store relation 2. We are going to talk about how does the system store those information. But at the bottom, right, all your information are there, stored as a whole bunch of files. And at the top is where the user start to interact with the system. So the input is a SQL query. The output is a relation. So how does database system make this happen? Like most of the computer systems, A database system also have multiple layers, and that's the beauty of system research, is really try to come up with these different layers of abstraction. So the database system that we are going to talk about in this course has the following components, and we are going to go through them one by one in the next couple of weeks. The first layer, over your hard drive, is something that we call disk manager. And then over the disk manager, there is something called the buffer pool manager or buffer manager. And then over that, there's another layer called access method. There's another layer called operator execution layer. And then there's the query optimization layer. So the database system that we are going to talk about contains these 5 different layers. And the structure of the lecture in the next couple of weeks is that we are going to go all the way from the bottom to the top to really think about how to construct a relational database system. So now let's go through at a really high level what each of these layers try to do. If you think about computer systems, right, the beauty of this course is probably the first time you start to really open up a computer system to think about what that looks like. So in the bottom, right, so every single layer, the goal is really try to abstract away some complexity of the lower layer to make sure whenever you are building this very complex system, you do not need to consider all the details at hardware level. Every single time you move up a single layer, you start to abstract away some complexity. So that's kind of the art of designing computer systems. So in the bottom layer, disk manager, what are the complexities that we are trying to abstract away? So essentially, the job of the disk manager, I mean, as the name implies, is try to interact with disks, right? It's try to manage all your hard drives. For example, it's try to allocate pages on your hard drive. It's try to delete pages on your hard drive. It's try to fetch pages for the upper layer from the disk. The goal is really try to make sure all the other layers that's above it, the buffer manager, access method, whatever, right, will not interact with the disk directly. All the complexity that you have in fetching a page, allocating a page, are managed by the disk manager. Everything above it will actually, they do not have information about your hard drive. So that is the goal of this layer. And then you move one level up. So the goal of the buffer manager is really try to make sure that to hide all those complexity you have in managing this storage hierarchy. Okay? So you have your storage, you have your disk, which is much larger than your main memory. But whenever you are writing code, you actually do not want the upper layer to manage this hierarchy. You actually want to hide that complexity from the upper layer. So essentially, the buffer is essentially the buffer manager try to maintain an in-memory buffer such that all the upper layer, right, have the illusion that your data is already in memory but not on disk. It's try to abstract away the existence of this storage hierarchy. So essentially, everything above it, whenever they are accessing data, the data is always in the memory. And the goal of the buffer manager is to make that illusion happen. So how does this buffer manager interact with the upper layer? Essentially, whenever the access method layer say, okay, fetch me a page, right? So buffer manager will say, okay, let's see whether this page is already in memory or not. If not in memory, I'm going to fetch it using my disk manager from my hard drive to the buffer and serve that request. If that page is already in main memory, I'm going to return that for you, right? So it's going to take charge of updating a page, right? So on and so forth. Now we can move one layer up. Now you have this buffer, okay? So everything above the buffer manager actually doesn't know too much about your hard drive, about your storage hierarchy. It just know I can fetch a page. And whenever I fetch it, it's already in main memory. Then I can do something like with it. So another layer over it is called access method. Essentially, try to provide different ways that you can access data from a relation. So the beauty is, once you reach this access method layer, you start to have the notion of a relation, right? If you think about buffer manager and disk manager, they are actually managing a much lower level abstraction, which are the pages, a chunk of data you store on your hard drive. Once you reach access method, you start to have a higher level notion about the relation. And the goal of the access method layer is really try to provide different ways that you can access your data. For example, one access method could be sequential scan. Okay? I have my information stored on my hard drive. I sequentially scan it. Okay? I fetch page 1, page 2, page 3. I sequentially scan for every single tuple. I do something. Right? This is one access method provided by the access method layer. You could do, for example, B-tree index. You could build an index, and you scan the index, right? You could say, yeah, so let's build a hash table, right? So I could sort all my tuples in this relation, right? So on and so forth. At this level, the interface is provided for the upper layer are all those kind of access method, right? So if the operator execution layer try to do something for your data, essentially, it will not try to fetch a page. It will say, OK, I know there are two relations. Sort this relation, sequential scan that relation. So that is a relationship between operator execution layer with the access method layer. And how does access method layer make that happen? Right? It's going to interact with a buffer manager to fetch the pages. Okay? And then you can actually move one layer up. And then you reach the operator execution layer. At this layer, you start to have even higher level of abstraction. You start to have your relational algebra operators. At this layer, you start to have the notion of join, projection, select, so on and so forth. All those relational algebra operators that we talked about before the Easter break is going to be served by this layer. Essentially, if you think about how does this layer interact with the query optimization layer, the upper layer, the query optimization layer can directly use all of those relational algebra operators to say, OK, these are two relations, join them. Okay? This is an interaction between query optimization layer and operator execution layer. And then once you have that request, what would this operator execution layer do? It will say, OK, you want me to join these two relations. What I'm going to do is to call the access method layer to say, OK, I need to join these two relations. The thing that I need to do is sequentially scan this relation and sequentially scan that relation. And for every pair of tuples, I join them together and check the condition. And then once the access method layer receives that request, it's going to interact with the buffer manager to say, OK, I now need to sequentially scan this relation. To do that, I need to fetch page 1, give me page 1. After that, I need to fetch page 2, give me page 2. And the buffer management layer is going to receive those requests of fetching pages and check whether they are in the buffer or not. If they are not in the buffer, it's going to interact with the disk manager to try to fetch that actual page from your hard drive to the buffer. So that's actually what's going to happen all the way from the top to the bottom when you issue some SQL queries to your database system. So that's the beauty of it. And then you can actually move one layer up. Right? In access method, you know how to access your data. In operator execution layer, you know how to run those relational algebra operator. At the query optimization layer, this is actually a layer that takes as input your SQL query. Okay? And then it's going to translate that into a tree of relational algebra operators. And we are going to call that a query plan. Okay? The goal of the query optimization layer is that given the SQL query, and try to find the query plan that is, hopefully optimal. In practice, it's not the worst. OK, so you try to find the query plan that hopefully is optimal. Okay, so once you have that, you actually have the plan about how to answer this query, and then you go all the way from the bottom of the tree to the root, right? And whenever you go one layer in the tree, you actually say, yeah, so here I need to do this relational algebra operator between over these relations, and then you start to call this operator execution layer for that. So as you can see, right? So this is a multi-layer kind of system. Every single time you move from the bottom to the top, you kind of start to hide away a whole bunch of complexities that you do not want the upper layer to manage. All the way from disk manager, right, you hide away the existence of different heterogeneous architecture of your hard drive. And then to the buffer manager, you do not have this storage hierarchy anymore. When you have the access method, right, and like you start to introduce higher level abstraction about how to access your data in a logical way, right? And then you start to have relational algebra operators, and then you start to have a query plan. So that is actually how most of the database system you have today actually works. So today we are going to look at the bottom layer, okay? In the next couple of weeks, we are going to go all the way from the bottom to the top. Now let's think about the disk manager. And the goal of today is really try to understand how does this component actually work. So before we talk about how does that component actually works, so like designing most of the computer systems, right, it's all about a cost-benefit analysis, okay? So the reason, one reason, that building system is actually a scientific effort is you need to understand the trade-off space. There's no design that performs better than all the other design in all the scenarios, okay? So what you are going to do in building a computer system is really try to understand, first one, what is the assumption you are making on your workload, because that's going to have a really significant impact on your design. And second is, what is my bottleneck, okay? What are the really important factors that actually slows me down? Once you understand that, you start to have a design of the system to really accommodate that bottleneck. So this is the way of thinking about building computer systems. So before we talk about how does a real database system actually works as a disk manager layer, let's try to understand a fundamental bottleneck that we are actually trying to accommodate in building such a system. And that brings us to the second topic that we are going to talk about today, which is the storage hierarchy. If you look at the last 50 years of database system research, most of the communities actually try to deal with the storage hierarchy. So essentially, right, if you look at all those assumptions, you already know what storage hierarchy actually looks like, right? So all data stored on hard drive, right? Disk is larger than memory, disk is slower than memory, right? Disks have different access patterns. You start to see this two-level structure. But in real systems, there are actually more. One fundamental system limitation for disk-oriented database architecture is actually this storage hierarchy. If you think about what that is, right? If you are writing a Python program or Java program, whatever you are doing in the first year, the dream of most of the programmer is, okay, I have a huge piece of memory, has the following property. It's private, it's really big, okay? And it's really fast. And whenever I just restart it, I will not lose my data. Someone put the plug of the device. When I reopen it, it will not lose data. Right? It's not expensive. Okay? If I have this, the database system you are looking at today will be very, very different. So the reason we have this multi-layer abstraction for database system is the thing on the left-hand side is not true. It's really great, but it's not true. The reality we have look like this. You do not have this homogeneous piece of memory. Instead, you have this hierarchy. Okay? From the bottom to the top, the moment you are moving to the top layer, your storage become faster, become more expensive, but also become much smaller. Okay? At the bottom, you have your, for example, you have your tape. And then you have your hard drive, you have main memory, you have your L2 cache inside the CPU, L1 cache, you have a register. Whenever you are moving one level up, sometimes you have one order of magnitude faster access. But on the other hand, you could also become much, much smaller. On the other, the other side of the coin is also become much more expensive, both in terms of how much money you need to build that, and also how much power you are going to consume in serving that. So this is the thing that we are going to deal with. Because of this reality, the disk-oriented architecture of database actually look like those multi-layer thing. Otherwise, if you have the thing on the left-hand side, you are going to have a very different type of system. So as computer scientists who are building systems, there are some numbers most of us need to not remember, but kind of have a feeling about how fast your machine can do things. Sometimes that could actually surprise you. So whenever you actually try to fetch data from your L1 cache to your register, we are talking about nanoseconds, something like that, okay? So if you have 2 gigahertz kind of CPU, you are talking about 0.5 nanosecond to actually load things from your L1 cache to your register. And then whenever you are loading things, right, from L2 to your register, right, we are talking about, yeah, like 10 nanoseconds, something like that, right? And then you can actually go all the way down, right? Whenever you have main memory access, you are fetching data from main memory to your CPU. We are talking about like 100 nanoseconds, something like that. And then whenever you have information sending through the network, it can become slower, right? Whenever you are reading something, right, like reading 1 megabyte from memory is going to cost you that, right? 200 like a millisecond, something like this, right? So whenever you have this disk access, you have like orders of magnitude slower access, something like this. So these are some constant, right? You don't want to remember that, but you need to have the feeling about those, right? About how fast your machine can actually do stuff. So and in reality, right? So something that we to get some feeling to actually appreciate the structure of a database system is assuming you have a CPU with like a 2 gigahertz, something like that. Every single CPU cycle, okay, translate to like 0.5 nanosecond, something like that. And usually your main memory, whenever you are fetching some information, right, to actually bring that piece of data from the memory to your CPU, it usually costs, for example, like 60 cycles or 100 CPU cycles, something like that. It's like that order. Whenever you have your hard drive, okay, so assuming you don't have, we are not talking about SSD, we're talking about those things that actually rotate, okay? So we are talking about every single time you actually move a piece of data from your hard drive to your CPU, that's like 10 million kind of cycles, something like that. If you look at those numbers, if you want to build a system that's fast, what do you need to do? You need to really optimize the I/O between the hard drive to the CPU to really keep your CPU busy. Because if you look at those numbers, your CPU can do a lot of things. Every single time you have one CPU cycle, right, you can run like at least one instruction, right? Sometimes more, okay? So, and then if every single time I'm bringing data from hard drive to the CPU costs my 10 million cycles, what am I going to do when I'm waiting the hard drive to bring data from hard drive to the CPU, right? If you do not optimize your system in that way, you are going to waste that 10 million cycles, just wait for data movement. So the game that we are going to play in the next couple of weeks is actually try to make the CPU as busy as possible by changing the design of the system, by changing the algorithm, by changing how you represent your data, all those type of things. But fundamental thing that we want to make sure is your CPU is as busy as possible. Because if you look at all those numbers, your CPU are all really waiting for you to get the data, okay? So this is another kind of like story hierarchy, right? So like in this case, there's actually another layer in the middle, right? You start to have those like SSD, those type of things that's actually faster than your hard drive, but slower than your DRAM, something like this, right? But things still hold, right? Reading data from your SSD is faster than your hard drive, but sometimes actually costs, for example, like 1 to 2 million cycles, right? So the game is the same. So what start to change is you have a different trade-off space. The price that I pay waiting for you to fetch data from SSD to my CPU is actually lower than the price that you need to pay fetching data from hard drive to your memory. And because of the difference in price, the principle of thinking about the system design is the same, but you start to pick different points in the trade-off space because I start to have different cost-benefit analysis. And story hierarchy is something that keeps changing, right? So this is actually one latest one, right? So there are actually a lot of interesting, fancy hardware people having today, right? For example, there's a new hardware called NVMe, right? Which is super, super fast, okay? And actually, whenever you have this new hardware, you start to redesign this memory hierarchy. Whenever you have this new memory hierarchy, the database community is going to jump in and have a new type of database system. If you look at what happened in the last half a century, from the research-wise, is people keep adopt your database system, redesign your system to really accommodate generations of this different hierarchy. So in this course, we are going to focus on the really simple one. That is, I have my hard drive, I have my DRAM, and I have my CPU, okay? So as you can see, even assuming these three very simple layers, there are a lot of things we need to consider from the system perspective, okay? But fundamentally, if you give me a new storage hierarchy, the system will look very different, but the way to design that system is actually not that different. Okay, now let's try to get on the same page about how hard drive works, because that's very important. So we are going to use that information again and again in the next couple of weeks. So this is a hard drive, okay? If you think about how hard drive works, so I think hopefully you'll never open up a hard drive, but this is actually what's inside, such that you don't have to. Essentially, there's all those disks, okay? And your information is actually stored like on those disks. So there are multiple of those, okay? So that's actually like something very important. So there are multiple of those disks. And then if you look from this angle, you start to have this ARM, okay? So essentially, whenever you are loading data from the hard drive to memory, that actually happens at essentially the head of this ARM, okay? So this is a place that you actually read data, okay? You think about hard drive as a two-dimensional coordination, like two-dimensional space. Every single data point that you have corresponding to a two-dimensional point on the disk, okay? Whenever you are loading something, what's going to happen is this ARM, together with the rotation, is going to navigate you to the right place. That's one step. And then once it reaches that step, it's going to read it, and then send that piece of data from the hard drive to your main memory, okay? So that's what's going to happen. And because of that, we start to have essentially a performance model. Oh, sorry, I need to change this. So then we need to have a performance model of the hard drive, which we are going to assume, and then we can reason about the performance of the system. So essentially, you have a whole bunch of disks. They keep spinning, okay? So, and we are assuming every single time, one of these head, okay, can only issue one read or one write at any given time, okay? And then every single time I'm actually reading something, I'm reading a block of data, okay? I do not read 1 byte. So for this hard drive that actually rotate, I read a block of data, for example, like 4 megabytes, okay? Whenever I'm reading something, I read this 4 megabytes. So given this, we can start to think about how fast it is or how slow it is to fetch data from the hard drive to the memory. Essentially, if you think about the time, there's the seek and rotate time, okay? We call that TS and TR, which actually is the time that you need to rotate your disk and also move your ARM to the right position, okay? And then we have this transfer time, which is actually the time you need to actually load that piece of data from your hard drive to your main memory. So whenever I access something, it's always the summation of seek and rotate and the transfer time, okay? So assuming I have random access D times. That is, I have my data stored in D different random places on those kind of disks. There's no pattern in where my data is stored. I do random access for D times. What is the cost? Right? In this case, every single time you have one access, what you need to do is you need to pay 1 unit of seek and rotate. Because it's random access, I don't know where it is. Every single time I have access to my data, I need to seek and rotate, okay, to find the right place. And then you transfer your data. If you have d random access, you need to pay d times the seek time, rotate time, and the transfer time. Another thing is assuming you have those sequential access, which means that the data I want to fetch, they all store together. Okay, they store actually like all together on the disk, and then I want to do sequential access for d times. Right? In this case, what's the difference? The difference is I only need to seek and rotate once to really find the right place in the beginning, right? And then for all the other access, I know where they are because my arm doesn't need to move, and my disk keeps spinning. The moment the disk rotate, I know, okay, this is my next batch of data that I need to fetch. In this case, when you are talking about sequential access for d times, right, essentially you pay 1 unit of seek and rotate, and then you pay d unit of the transfer time. So this is actually 2 interesting access patterns. Right? So whenever we are saying, yeah, the disk favors different access pattern, this is what we mean. So for these 2 access patterns, right, they actually fetch the same amount of data. They fetch d blocks of data. But they are very different time. So if you think about a real hard drive that actually rotate, your seek and rotate time is actually in the order of 10 milliseconds, something like that. And if you think about transfer time, we are talking about if you want to read like 8 kilobyte, so the time I need to move that 8 kilobyte from the hard drive to the main memory is like 0.1 millisecond, something like that. If you think about this, how long would that take for you to actually read like 1,008 kilobyte blocks, right? So it's a difference actually pretty big, right? You can actually do the computation, right? You can see this orders of magnitude difference between sequential access and the random access. And because of that, we need to design algorithms to answer your SQL query that actually do more sequential access and do fewer and fewer random access. So this is actually the fundamental thing, like why database system look like today. So, and you can actually see that in practice, right? So this is actually actually very interesting YouTube video like about this. So essentially, so I think what they do is they have this 3 different type of devices. So on left-hand side is a hard drive, okay? In the middle is an SSD. I mean, yeah, you can look at that for fun, right? So we are not going to consider that in the course. And then on the right-hand side, that's your main memory, okay? It just simply mounts the memory as a hard drive. And then you try to test the speed, okay? So for every single row, right, so it's different access pattern, right? So the first row is sequential scan, okay? So the second row is you have random access, but every single time you access data, you're actually loading 500 kilobyte. And then the third row is you have random access like 4 kilobyte, okay? So, and then for the first column is your read time, you actually read data. For the second column, you start to write data. And then you can actually see the difference in their speed, okay? So as you can see, on your hard drive, whenever you are doing sequential access, read and write data usually is like 100 megabytes per second, something like that. That's something you can get today. And then whenever you are doing those random access, okay? So the smaller the block size is, the slower the random access is. If you are having random access on a block that is 500 kilobyte, right? So the amount of data you can fetch every single second on your hard drive start to drop, right? You become like 60 megabytes per second, for example. But whenever you are reading those very small piece of data, for example, you have random access over 4 kilobyte block, you can see your throughput become, for example, 0.7 megabytes per second, right? So that's the difference. So this is going to change your algorithm design. Whenever you are actually trying to answer a SQL query, you prefer sequential access. If you cannot have sequential access, you prefer those random access with bigger block size. If you cannot do that, you start to have those random access with really small block. So that's the difference. On the other hand, if you look at your main memory, you can see the difference. And there are differences, but difference is actually not that big. Okay? If you are doing sequential access on your DRAM, this is actually not that fast, but you have those like 5 gigabytes per second, something like that, fetching information from your DRAM to the CPU, compared with this 100 megabytes per second from your hard drive to your CPU. Okay? And then whenever you are reading a bigger block, like 500 kilobytes, you don't really see a difference between sequential access and random access. Okay? So, and of course, when you start to do this random access of a very small chunk of data, like 4 kilobytes on your DRAM, you start to see this 1 order of magnitude decrease in throughput. So this is what we are going to deal with. Okay? So these are the numbers that we are going to play with to actually design our system, design our data layout, design our algorithm to make sure this difference doesn't matter too much in practice. So that's the game. So in this course, right, we focus on simple hierarchy, hard drive, DRAM, and CPU. So because DRAM and CPU is actually dominatingly faster in this setting compared with hardware to DRAM, whenever we are thinking about the performance of the system, we actually will focus on how to optimize data movement from hard drive to DRAM. And you can see this from the previous slides, right? The data movement from DRAM to CPU is really fast, right? So I mean, in practice, it will make a difference. But if you do not optimize the I/O from hard drive to DRAM file, that won't matter too much at all. Okay? So this is actually what we are going to talk about in this course. We are going to actually count how, try to optimize data movement from hard drive to DRAM, okay, in this course. Okay, now we have our assumption on the architecture. We have our assumption on the bottleneck. And then we can start to actually think about how to build a system to actually manage your hard drive. So this is the lowest layer of a database management system. Essentially, all the higher layer is going to call this layer to actually allocate or deallocate a page, to read and write a page, something like that. So how to build that layer? Before we talk about how to build that layer, let's try to agree on what is that layer try to do, like really, really precisely. So essentially, if you look at most of database systems, they are actually trying to store the things as a whole bunch of files on disk. Some of database systems, like Sqlite, which we are going to see, actually store the data as a single file. The whole database is actually a single file. So for some database systems, for example, Postgresql that we are using in this course, they are actually going to store the database as a collection of files. Okay? But whatever it is, there are files on your hard drive. So, and today, many of database systems actually use the file system provided by the operating system to actually manage those files. Okay? So that's why, like in our system architecture, do not see file manager. Okay? So often we can just use whatever provided by the operating system. So there was a time, like 20 or 30 years ago, database people actually built a custom file system for a database. Okay? So there was a time people tried to bypass the file system provided by the operating system. But today, I think most of the modern database system, well, most of the, actually many of the database system actually just use the file system provided by the OS, for example, Postgresql. Okay? So what do we want to have from the storage manager? Right? It's actually responsible in actually maintaining a database file. So storage manager organizes the file as a collection of pages. Okay? And the page is a fixed size block of data. For example, 4 kilobytes or 4 megabytes. That's a chunk of data you put on your hard drive. Right? So, and the file contains a collection of those pages. And each page contains tuples, right? Contains the metadata, contains indices, right? Contains your log record, for example. And each page has a unique page ID. Okay? So now let's take a break. So in 15 minutes, we are going to show you actually how a page looks like in a real database system. Yeah, let's take a break. OK, so let's continue. See how database works. OK. OK, so let's continue. OK, so I mean, these are the principles, right? A database is actually maintains a collection of files, right? So, and each file contains a collection of pages, right, which contains a collection of tuples, right? So we don't need to, you don't need to trust me for that. We can actually just see what it looks like in one database systems, okay? So we are not going to do Postgresql because that's a little bit too complex. We are going to do a simple one called Sqlite, okay? So assuming that we create a database like Sqlite MyDB, right? So you can actually start to write SQL queries here. Let's say we create table with, for example, 2 attributes, right? So there's A with 1 character, B is another character, something like this, right? Then essentially you have one relation. I think hopefully everyone know this now, right? If you, so it's empty, right? You can actually insert into R values. For example, you can insert 1 tuple, A and B, right? And you can actually insert another tuple, for example, C and D. You can insert another tuple, for example, E, F, something like this. And then essentially, if you see what's in the table, right, this is what you have. You have 3 you have 3 different tuples, right? A, B, C, D, F, right? It's as simple as that. So now let's think about how does database make this happen. Okay? So the beauty of Sqlite is essentially the whole database is a single file. You can actually open this file that we have. This is your database. Okay? And this file actually have structure, right? We can actually see that here. This file has structure. Okay? Now looking at this, let's try to understand how does Sqlite actually store your database as a collection of files. So so essentially this is the address. So first attribute, you guys know how to read this, right? So the first attribute is the address. It starts from 0, okay? And then in the middle, it is the content, okay? And then on the right-hand side, it just makes sure it's more human readable, okay? The real data is the thing in the middle. So first thing is, what is a byte? Okay? If you look at the content, right, what is a byte? I want to try. So what is a byte here? So essentially this thing, for example, this is this 5 and 3 together, okay, is the first byte of that file. Make sense? Okay? Because there are 256 choices, that's 8-bit, okay? And then, essentially, if you look at this, from here, 0, 0, 0, all the way down, to 1,000, 10000, okay? So this is how many bytes. From 0 to here is how many bytes? I want to try. How many bytes? It's 4 kilobyte, right? It's 4 kilobyte. This is 16, yeah. So essentially everything above it is 4 kilobyte. If you look at the content here, you can see this interesting structure of this page. This is actually one page. And you are going to see that structure in many of the examples in this course. That is, the top of the page actually has information, right? What information do we have at the top of the page? You say, yeah, so this file is a Sqlite format 3. It's say, yeah, what type of database do I have here, right? And then the middle part of this page is actually empty, okay? As you can see, it's actually empty. And then the tail of this page has content. So this is actually a log. This is actually the relation that you just created, right? So this is a binary representation of the SQL query that you wrote. Define the schema, right? Serve as history, right? This is actually one chunk of data. This is the first page. You can see page could contain metadata, right? Contain what type of database it is, right? Maybe contain log, contain schema, all the type of things. So starting from this line, you actually start your second page inside your database, okay? And then if you look at what you have, like in the beginning, it has a whole bunch of metadata about this page. If you go to a Sqlite reference, you are able to know what they actually mean. But you do need to go to the reference to know what this means, right? If you look at the tail of this page, what's interesting, remember that 3 tuples have been inserted into the database, right? A, B, C, D, E, F. They are actually encoded at the tail of this page. This is actually where your data sit. This 61 corresponding to the value A that you inserted, because that's ASCII for A. Followed by that, this is B. Essentially, this is one tuple inside your relation, okay? And then the second tuple we inserted is actually this thing, 63 and 64. So what's in the middle are actually the things that databases are using to actually separate these 2 tuples, okay? So there's no magic. Essentially, whenever you are running a SQL query, underneath the cover, there is a binary representation of your data inside your database. And then the third thing that you inserted, 65, 66, right? This is the E and the F, the third tuple that you inserted, okay? So to convince you this is really the data, we can actually try to change it and see what our, so a disclaimer, do not do this on your database, okay? So they just try to convince you that I'm not trying to trick you that database is storing things as a file, but do not do this on your database, okay? It's very dangerous. You can just change it to some other thing. We refresh. You reopen your database. What's the name of the relation that we have? R, right? Okay. You do that again. This is what you have. As you can see, the third tuple start to change value. So there's no magic, okay? All the information you have inside your database is actually stored inside the file. And then we can actually see there are 2 different types of pages inside the file. There are those pages corresponding to data, which is the second page in Sqlite. Why it corresponds to data? Because the moment I change it, it's kind of reflected in my database. Again, don't do that on any real database, okay? Your database professor didn't teach you how to do that, okay? So, and then the first page contains metadata, contains schema, all those type of informations, right? This is actually how database works, right? So it's not that abstract. It's actually something that you can actually play with, like all by yourself. Okay, now we see how Sqlite actually looks like at the file level. So the job of storage manager is really try to manage this collection of pages to really form the abstraction of a relation. Essentially, it stores relation as a collection of pages, right, and that we call file, right? And each page, we hope to store a collection of tuples. And we already see in Sqlite how Sqlite actually does it. And then there are 2 fundamental questions once you try to build such a storage manager or disk manager. The first question is, how does the database system actually manage a collection of pages? I have a collection of pages. What data structure should I have to maintain that collection of pages? In Sqlite, that structure is a single file. But in PostgreSQL, there could be other abstractions, okay? So the second question is, how does database actually store tuples on each page? Again, we see how Sqlite does it, right? From the tail of the page, you store tuple 1 by 1, and you separate them by some magic binary thing we don't really understand, right? So that's how Sqlite does it. But again, PostgreSQL might do different things. But these are the 2 fundamental questions that we want to understand, to really understand how can we manage this collection of pages. So the roadmap of today is we are going to talk about one, not naive design, but one natural design to answer that 2 questions. Given a relation on the left-hand side, we are going to think about how to manage them, right? How to put that relation into a file, content collection pages, and how to organize those pages. And then given a page, we are going to open it up, right? To really try to understand, yeah, how can we put tuples inside the page? And then we are going to talk about how should you, not should you, but one way for you to organize data, represent the data of a single tuple. Okay, there's a tuple representation, there's a page representation, there's a file representation. Okay, and we are going to go the direction from the left to the right. Okay, we are going to actually go from the top to the bottom in the abstraction part. Okay, now I have a relation. I want to store them as a whole bunch of pages. So the first abstraction that we need to introduce is the notion of file. Inside database, there are actually different ways for you to organize a file. But one way is to organize them as a heap file. Okay? So this is the interface of heap file from a very simple database system. It's just really helpful to make sure we understand what a heap file really tries to do. Essentially, a heap file is an unordered collection of pages where tuples are stored in a random order. This is the assumption of a heap file. So whenever we talk about a single tuple, it is associated with a record ID. And for each record ID is always a pair, contains the page ID, which page this tuple belongs to, and also the slot ID to make sure whenever I give you a page, you know how to fetch the tuple. So the record ID is always a pair. So to support this record level operations, right, what do you need to do? You need to keep track all the pages in a file, right? Or you need to keep track of the free spaces on the pages. You need to keep track of the record of each page. So for each of this, we can actually talk about how database actually do it. But again, just to make sure we understand what heap file can actually provide, let's try to read this interface together, okay? So this is actually an object for heap file. As you can see, right? So it actually has one method called getRecordCount, right? Which give you how many records or tuples do I have inside this file, okay? That's one function you need to implement if you want to implement a heap file. The second one is insert a record. I want to insert a record into this file. To do that, right, so I give you the pointer to the record that I want to insert, and then I give you essentially I return the record ID, okay? I give you the content, you insert a tuple into the file, you give me the record ID, which is a pair of page ID and also slot ID. And then I have another function called delete record, right? If I give you a record ID, you can actually delete it. There's an update record, right? Very natural. Give you a record ID, give you the a new record, you update it. Get record, right? The input is record ID, the output is a record with that ID, right? And then there's another method called scan, right? Which says that, okay, so I have all the tuples, I want to do a sequential scan of all those tuples. And you return all those records during the scan process. So this is a very simple interface of a heap file. Now let's try to understand how can we build that. So there are two ways to actually implement a heap file. The first way is to think about that collection of pages to be organized as a linked list, okay? And second way is to think about those as something called a page directory, which we are going to talk about. So first way is relatively simple, okay? So, okay, you have a whole bunch of pages. I organize all my pages into two different categories, each category corresponding to one linked list. I have all those free pages, the page that's empty, as one linked list. And then I have all my pages that's not free, right, called data page, the yellow thing, right, as another linked list. Right? In this case, right, given a page, I know where to find the next page, I know where to find the previous page. Essentially, I have a way to enumerate all the pages inside this file. And then I have a single header page. That is where I start. Okay? So this is one way to organize all those pages. If you think about this data structure, right, how should we implement each of the functions that we want to implement inside a heap file? Okay? How to get the number of record, right? The first one, get record count. Get number of record or tuples I have inside this file. Well, there are multiple ways you can implement that. You can put that as a metadata in the header page to say this is the number of tuples I have in this file. The moment you call this get record count function, I fetch the header page, which is one page I/O. You need to fetch that from disk to memory. Okay, one read. Yeah, you have that file inside your memory now. You read that number, you return it. Okay. Another way to implement that is you can actually sequential scan all the data page. You start from your header page. You find your first data page. You fetch that. There's a second I/O. And then you read all the tuples. You count how many tuples you have. You go to the next page. It's possible because the whole thing is a linked list. You fetch all tuples, and then you count. Okay? So usually people do the first one because it's cheaper, but nothing stops you from doing the second one. Right? How can you insert a record? Right. In this case, right, so what should you do? You start from the header page. You say, yeah, I want to insert a record. You need to find an empty slot in the data page that you can insert like this record. You start from your header page. You go to your data page 1. You read it. You see, yeah, whether there are empty slot. If the empty slot, I put data in, then I write it back. So 2 data I/O for data page 1. And then you succeed. If data page 1 is full, you go to data page 2, you go to data page 3, until you find a slot. If you reach the end of the list, but you still cannot find a slot, then you go back to the header page, you fetch the free page 1, then you insert that tuple, and you put the free page 1 as data page 4, right? Move that from the first linked list to the second linked list. So very natural, right? Once you have this data structure, it gives you a way to enumerate all the pages. Once you have that functionality, you are able to implement all the functions we have inside a heap file. But this is not the only way. So second way, which is actually a more popular way to organize those pages, is to use something called a page directory. Okay? So the high-level idea is I do not maintain this 2 linked list. I want more freedom in navigating all those pages. So what I'm going to do is to have a whole bunch of header pages. And inside each header page, I maintain 1 tuple for each page. Okay? I have a whole bunch of data pages, data page 1 to 3. They corresponding to different tuples in the header page. And that tuple contains a whole bunch of information. For example, how many free slots do I have for that page, right? So on and so forth. And we call that the page directory. So given this, how can we implement this, right? So for example, if you want to say insert record, how can we implement that function? What we are going to do is to fetch the header page, go through the directory. Instead of going through pages to find a slot, we go through the directory to say, yeah, the first page, how many slots do we have? Second page, how many slots do we have? You find the first page in the directory that have a free slot that's big enough for your tuple. You fetch that page. You know where it is because you are actually storing the pointer to that page. You fetch it, and then you put the record in. You put the page back. Okay? So similarly, you can implement all of these things. So as you can see, this one gives you actually kind of more freedom to really try to navigate all those pages. When building computer systems, it's very interesting to have different designs and put them side by side and try to reason about their trade-off. So this is actually an easy one because usually I think most people agree the second one is actually better in most of the scenarios that we care about, right? So in the naive implementation using linked list, right? So there will be actually free spaces here and there, right? Because it's very hard for you, whenever you delete data, right, it's very hard for you to optimize your data layout in a global way, right? So you have those free slots here and there for the first design. For second design, I mean, there could also be free slots here and there, but it's usually easier for you to fill those holes. So in terms of the performance, right, so one thing that we are going to do in the next couple of weeks is really try to reason about the performance of the system. So now let's do this exercise using this very simple example. Okay? So assume, you always start from assumptions. Assume the directory, the header page, fit in the memory and is already in the memory. Okay? So assume that's true. Assume the number of pages equals to D. Okay? And assume pages are randomly allocated on disk. So this is a worst case scenario of what can happen for a heap file organized with linked list. Is all those pages, all those data pages, are allocated randomly on your hard drive. Okay? So let's assume that's true. What is the performance for a single insert of a tuple? It's very simple. Okay? So I promise you next week it's going to become way more complicated than this. Okay? But let's do this simple thing. What is the cost of insert a single record? Well, in this case, what do we need to do? You need to, okay, so assume data page 1 has a free slot, okay? What is the cost? The I/O cost. So what do we need to do? The header page is already in memory, so I do not pay I/O, I can access data there. That's our assumption, okay? It's not always the case, but that's what we assume to be true. Given that, I know where the first page is. I fetch the first page. I have, what do I need to do? Because the page is randomly allocated on hard drive, I need to pay 1 unit of secant rotate to make sure the arm and the disk are rotating to the right position corresponding to page 1. And then I read it. I pay 1 unit of transfer cost. And once I have that, I realize, okay, there's a free slot. Great. I put the tuple in. The page is already in the memory. I put the tuple in. There's no I/O cost. And then I write it back. Okay? So essentially, assuming page 1 has a slot available, you are paying actually 1 unit of secant rotate plus 2 units, assuming read and write are the same, which is not true, actually, right? And but roughly like 2 units of transfer time, because you need to have 1 read, have 1 write. So what is the performance of funding a record in expectation, right? So like in this case, right, so for example, I want to fund a record by a non-record ID value. For example, I have a whole bunch of students in the relation. I say, yeah, give me all the students give me 1 student who is like, for example, 20 years old, right? So in this case, what can you do? I mean, there's nothing you can do other than sequentially scanning all the tuples in your file. Assuming in expectation, you find that in the middle, you have D pages, you need to sequentially, you need to scan, not sequentially because they are randomly allocated. You need to scan D over 2 number of pages in expectation. For each of those pages, what you need to do is you need to pay 1 unit of secant rotate because those pages are randomly allocated, and then plus 1 unit of transfer. Okay? So this is actually the expected performance. I'll try to find the record. So what is the performance of doing a scan in this of your data? I scan every single tuple. Okay? So in this case, right, it's a D number of data pages multiplied by 1 unit of secant rotate plus the transfer time. It's simple, right? Any question about this? Any questions? Okay, it's going to get really complicated really fast in the next couple of weeks, okay? Now let's look at this thing. Okay, so let's do this exercise, right? So counting I/O is one thing we are going to do in this course. So assume we have this data structure, page directory. Assume the directory, all the blue pages, those like header pages, fit in memory and it's already in memory. Okay. assuming the number of data pages is equals to D, and assume, in this case, pages are sequentially allocated on disk. Right? This is actually the best case scenario you can have. So what is the performance, the I/O performance of inserting a tuple? In this case, what would you do? You are going to actually scan all the header pages and try to find a page with empty slot. Because the header page is already in memory, you do not pay I/O cost. Great. You find the page, and then you fetch it. This fetch, do you have seek and rotate? You will, right? Because all the data pages are actually put together in a sequential way, right? But the header page might be somewhere else, right? You have one seek and rotate, and then you read it, you put the record in, you write it down, right? Essentially, we are talking about 1 unit of seek rotate plus 2 units of transfer time. So as you can see, this is already faster than the previous thing. The previous thing, we get the same performance, assuming the first page has a free slot. If the first page does not have free slot, the first one is going to be actually more expensive. So what about to find the record, right? So in this case, because all those data pages are stored in a sequential way, you are doing sequential access, you only pay 1 unit of seek and rotate, because the moment you find the right place, you can keep reading while the disk is spinning, okay? So you have 1 unit of seek and rotate, plus, in expectation, D/2 many of transfer. Okay, makes sense? What is the cost of scan, right? In this case, right? 1 unit of seek and rotate, you find the beginning of the data chunk, right? And then keep reading, right? 1 unit of seek and rotate plus D unit of transfer. Okay, this is a very simple exercise. We are going to do this for way more complex things, but yeah, we just want to make sure everyone's on the same page about what we are trying to do. Okay, this is how to organize a file, right? Yeah.
For the insert case, would we also have an additional rotate? Because by the time we change the data, we still have to wait for one rotation before we get inserted back?
Yeah, so that's a very good question. Yeah, so that's a very good question. We kind of assume the disk has a buffer. Your write will be put back when the disk happens to rotate to that place. So okay. In this, okay. Let me see what to say. On real hardware, highly likely this is what you pay. Okay, so because on real hardware, what's going to happen is you are going to batch all the writes. It's not like I want you to write a page. You actually write that for real. Essentially, you are going to batch all the write, and you are going to write it whenever it's faster. So in practice, highly likely this is what you get. I mean, or like this is what you would expect, right? But in practice, if every single time you write it, you say, you must write it, like I force you to write it, then yes, you pay 2 times seek and rotate. Yeah, okay. Okay, great. Any questions about this? Any questions? No? Okay. Now we know how to organize a collection of pages. The second thing that we need to understand is really try to understand how can we organize the information on a single page, right? So now let's open up the second layer of abstraction. So a page, as you see in the Sqlite example, right, it contains actually 2 components. There's the header in the beginning of the page, okay? And then there's the data. So what's interesting about the page, like often what people do is a header is going to grow from the beginning to the tail, okay, like to the end. And the data is going to grow from the end to the beginning. That's why in the previous example, the middle part of this page is often empty, because you start to put data from the end to the beginning, and you start to put the header from the beginning to the end. Okay? So this, I mean, you could do other things, but this is often what people do in practice. Just header this data. And each page contains a header of metadata, for example, page size, right? How big this page is, right? So the version of the database system, right, we saw in the first page of Sqlite, right, is there, Sqlite 3. So what compression or encryption thing that we have on the data, checksum to make sure we cannot change the data there, right? So like all those information in the header. So this is one example interface of a page. Okay? So to really understand what we need, like from a page, precisely. So essentially, right, from given a page, you have one method to give you the next page, give you a previous page, to make sure you can actually link a page together, right? To make sure whenever you want to sequentially scan the file, you know how to scan it. Okay? And then you can set the next page, set the previous page, you can get the page number, right? And you can actually insert a record to a page. Okay? So here, you are given the content of the record and the page. You say, yeah, this is the page. Put that record into this page and get the record ID back. You can delete the record. You can get the first record. You can get the next record. You can get the record, right? All those type of things. And you can get the available space in this page. It's pretty natural interface, right? So now let's think about how to implement that. So there are multiple things that you can do. The easiest thing you can do is you could have a page layout look like this. I have a header, and then I partition all the data space into a whole bunch of fixed size slots. Slot 1, slot 2, here I have 5 slots. Okay? And then they can hold tuples. So in the header, I also keep track how many tuples that I have in this file. For example, if I say, yeah, insert a tuple T1 into this page, what you can do is you can say, yeah, now let's try to find an empty slot. Here I'm going to find the first slot. It's empty. I put that record in. You insert another tuple. Here you're actually going to occupy the second slot. You insert another tuple, the third one. You can delete a tuple. You sequentially scan all the slots. You get the second one, right? And then you remove it. Then you have an empty slot. I say, yeah, insert T4. Then you have another one occupy the second one. So this could be one possible layout you have. Okay? So what's the problem here? The problem here is, of course, here we are assuming all the tuples have the same size, right? Which could be true in many cases, but could also be false in other cases. Right? In database system, we have string, for example, your tuple could have different size, right? So then this one could become a little bit tricky to manage. So another way that you can organize information inside the page is by using something called slotted page. So it looks like this. You still have the header. That thing doesn't change. And then the way you organize the data part of a page looks like this. You have a whole bunch of slots. Okay? So that's a slot array part. For every single slot is corresponding to one element in the slot array. And then every single slot element in the slot array have a pointer to the data part, which is the beginning of the data that you put into that slot. Okay? So for example, here, in this page, you have one tuple, which occupy, if you count from the right-hand side, the third slot, which have a pointer start from the beginning of the blue rectangle, right? So that's your data. If you want to insert a tuple, you could say, yeah, I want to insert tuple to the last slot, right? And then here what you can do is you can say, yeah, here's a pointer, point to the beginning of the orange data block, right? Something like this. And you can keep doing this like insertion, all those type of things. So this is another way to organize data inside the page. Essentially, every single record, right, is a pair of page ID and slot ID. And then each slot contains a pointer to the start position of each record, right? And then the interesting thing about this, you can actually move record on page without changing the record ID, because you are only keeping the slot ID, not the absolute position of that record, right? You can actually move the data around within a page without changing the record ID. Make sense? This is slot page, right, which is actually very natural. Now, another thing that we need to understand is now we know how to organize the page, how to organize the information within each tuple, right? Well, here we are assuming that tuple is a black box. Now let's open that another layer of abstraction. How to organize data inside tuple? Again, there are different ways, right? So if you look at the tuple, it contains a collection of attributes. And then there are two different types of attributes. So there are those attributes with fixed length, right? For example, integer, right? So like a date, right? So fixed length string, those type of things, right? They have the same length, like in this tuple. So you could just directly access those tuples. You can actually store them one by one, right? You know how to access them, right? Because you know the length of them, and you know how to do how to address them. The thing becomes tricky is when you have this variable length field. For example, you have string. Okay, the thing that people often do is to say, similar to a slot page, I actually put the length on pointer of that field as part of the fixed length field. And then whenever I reach that, I'm going to read that length and pointer thing from the fixed length field. And then I'm going to fetch the information. Okay? I'm going to put all those variable length tuple at the end of this tuple. Like the variable length field at the end of this tuple. So this is actually one thing that you can do, right? You access in two steps. You get the pointer, then you chase the pointer. So null value is often interesting. So what people often do is to actually to put a bitmap in the beginning of this tuple. Okay? For every single attribute, it's going to correspond to a single bit in the bitmap in the beginning of this tuple. If this field is actually, if this attribute is null, it's going to set to 1, otherwise set to 0. Okay? So essentially, if you look at the structure of a tuple, it's often look like this. You have the bitmap storing those null information, and then you have this fixed length field, okay? And then you have this variable length field, the payload. So that's often what happens in practice, in a very naive database system. So, and then this is one example for the field, for the fixed length field, right? So for example, you have the first attribute, have the length L1, you have L2, L3, L4, right? You know how to find the information, right? To find the third field, right? You have the base address plus the length of first field and length of second field. You know where to find the third field, right? So essentially that's fun. Whenever you have this variable length field, it's got a little bit tricky. So there are different ways you can do, again, right? So first way you can do is you can have a very special delimiter, right? You have this delimiter, you have this data for the first field, then you have another delimiter, you start a second field. You could do that, and there's nothing stop you from doing that. Another thing you could do is do the thing that we talk about, is you have this length and pointer in the beginning as a fixed length field, and then you point to the real data stored at the end of the tuple, right? If you actually compare these two different ways, right? So the second way is easier for you to fetch information because you know where the data is. The first way is a little bit hard for you to fetch information because if you want the second field, you kind of need to scan this tuple to find the second delimiter, right? And then you know where the second field is, okay? So that's the difference. So in this case, right, so we can actually look at one example to show you what PostgreSQL actually look like. So let's try to okay, let's try to go back here. Now let's try to open PostgreSQL, okay? this is my PostgreSQL. Let's create a relation. Okay, create table, again, R. Okay, 2 attributes. I insert into R values. First one from 0, 1. Oh, sorry. The second tuple, maybe 2 and 3. The third tuple, maybe 4 and 5. Okay, now I have these 3 different tuples, and there's no magic behind it. So what's interesting inside PostgreSQL is there are actually all those attributes that the system have, but do not expose to the user by default. Okay, but you are able to query it. One interesting attribute here is called Ctid. If you actually do this inside PostgreSQL, what you are going to have is you are going to get a result like this. The first attribute is a pair. Okay, this is actually the record ID of each tuple. Usually, PostgreSQL do not expose it to the user, but you are able to query it anyway. So as you can see, the first tuple here is being stored on page 0 because a very small relation. Okay, so only 1 page. I think that's reasonable. On page 0, slot 1. Okay, the second tuple on page 0, slot 2. The third tuple on page 0, slot 3. Okay, so as you can see, this is actually how database manage it. It's actually organize the whole thing as a slot pages, right? Essentially, for every single page, you have the slot and point to the data. So you can actually try to delete stuff. For example, you delete the second tuple. And then you rerun this. What would you get? In this case, if you actually run this, you are going to say, yeah, the second tuple disappeared. But you can see now there's a hole in the page, right? The first slot is full, but the second tuple is being stored on the third slot. Which makes sense, right? The moment you delete stuff, the quickest way for database to delete stuff for you is to set the slot to empty. Do not touch all the other data. It doesn't need to be, right? So essentially, now you have a hole in the page, okay? So that could cause problem in some scenarios, right? But if you just want to delete stuff, this is the quickest way. So how to fill the hole? That's another thing. Now, assuming I don't want this, I don't want a hole in my page for whatever reason. How to fill the hole? So inside PostgreSQL, there's an interesting command called vacuum. If you do this, what you are going to have is to reorganize your data. Not only filling holes inside your page, but if you have a page with a lot of holes, it could also reallocate data to other pages. The thing is really try to make sure your data after you run this vacuum stuff is as compact as possible. Okay? So here we have only one page. If you run this, I hope I typed it correctly, and then if you do that again, you can see this reorganization of data inside your database system. Now the second tuple is actually in the second slot. It's actually start to actually move like data, like both move the slot. I think it's going to actually move the actual data to make sure you have this free space kind of all together to make sure you actually hold more tuples. So this is actually what's going to happen, right? So this is actually how does a slotted page look like inside PostgreSQL. Also, how to reorganize this. Okay? Yeah.
If you had inserted the tuple after deleting, would it have put it in the empty slot that has just become empty?
I hope so. I don't know. No. No. OK, so I actually don't know what happened. Yeah. So I mean, so like this is a function of the implementation, right? So it could say whenever I have empty slot at the tail, I just put that in, right? Because that's very easy to insert. Otherwise, I need to sequentially scan all the slots and find the right one. So yeah, if I will build a system, yeah, and potentially can check is yeah. So I think what's happening is going to find. So assuming it's probably going to have one pointer point to the last non-empty slot, and then you just insert. Yeah. So simply faster than sequentially scan, like all the slots. Yeah, play with it. It's super fun. Okay. So and you can actually insert more data into this to have multiple pages, and you can actually see the behavior of the database system. Okay. Or you can like have a Sqlite and just play with a page layout, try to change things to see what happens. Okay. So that's all for today. On Friday we are going to move one layer up. Okay. So I'll see you guys on Friday.